Another interesting characteristic of water is its capacity to complexate ions. So, for example, and this is based on acid base. You have metal ions, and metal ions are what we call Lewis acids. And what we mean with Lewis acid, it means it's an ion, it's a compound, it's an atom that is capable of accepting electrons. And metal ions are all positively charged, so they are all lacking negative charge, so they are really quite happy to accept electrons. And water is what we call a Lewis base. And what do we mean by a Lewis base? Well, a Lewis base is a compound that has electrons that can donate. And water definitely has electrons that can donate, because if you remember what the structure of water is, the oxygen has 2 bonds with the hydrogens, and it also has electrons that are not being used for bonding with the hydrogens. We call those non-bonding electrons. So you have those electrons around the oxygen that are not are part of the oxygen atom. They are not participating in the bond. They are there, available to interact with other species. So when you have something like water, which is a Lewis base, it has electrons that can be donated. Find a species which is a Lewis acid, can accept those electrons, then you make what is called a complex. And this is a type of bond in which one of them, the Lewis base, the water, donates the electrons to the Lewis acid, the metal ion. And as you can see, for example, for aluminium can interact with up to 6 water molecules. So you still have aluminium 3 plus, is metal, the aluminium ion with 3 positive charges, and it is surrounded by 6 molecules of water. We call it's not only water, for example. You can have other compounds that have electrons that can be donated, can be surrounding that molecule of water. And for example, here you've got can be surrounded that metal ion. And for example, I have here a picture in which you have copper dissolved in water, and is copper with 2 positive charges, and is surrounded by this orange ball here, which is surrounded by 6 molecules of water. And then if you add a little bit of ammonia, the ammonia, which also has electrons that can donate and can also act as a Lewis base, will displace some of those water molecules, and then you will have a new compound, a new complex, in which the copper is surrounded by some molecules of ammonia, 4 of them, and some molecules of water, 2 of them. And we call this entity, this combination of the metal ion and the molecules surrounding it, we call it a complex. So a complex is just a metal ion surrounded by a series of molecules around it that are interacting with that metal ion by donating electrons. And we call these molecules that are surrounding that metal ion, we call those a ligand. So we say that water is a ligand, and it's a very good ligand that can interact with metal ions and form complex. And we normally call those ions, because we're talking about water, we talked about those ions are hydrated ions. So we talk about the process of hydrating an ion. How many molecules of water will it take to hydrate an ion of aluminium, or ion of copper, an ion of chromium 3, etc. Why do we care about this complexation, hydration, this interaction between the metal ions and the molecules of water? Well, because it gives rise to a very interesting and sometimes very complicated chemistry that determines what sort of, in what way those metal ions will be in the atmosphere, in the environment, and what sort of species will it make. So, for example, when you have an atom of iron with two positive charges dissolving water, you have it surrounded by 6 molecules of water, and that's a hydrated iron 2 ion. But if you have cyanide in the medium, cyanide can make really good complex, can make really good bond with the iron, so it will displace one of your water molecules, and it will make a new complex in which you have the iron ion, you've got cyanide, and the other 5 will still be molecules of water. So the cyanide goes in and one of these water molecules goes out, which is what this equation is trying to show. So we talk about ligands, and we say that water is a ligand and cyanide is a ligand, and that, you know, cyanide is a stronger ligand than water, is able of displacing one of the water molecules and replace it, and those ligands are just, it could be a molecule, it could be a neutral species, it could be an organic compound, it could be an anion, for example, a chloride, something that has a negative charge, that they have electrons. They have electrons that can donate and attach themselves to a metal ion, and we call those bonds coordinate bonds. What do we have as ligands? Pues they are sometimes they are anions. They have a negative charge, like for example a chloride anion, or a nitrate, or a carbonate, or the cyanide that I mentioned earlier. Sometimes, well, they are molecules, neutral molecules, like ammonia, for example, NH3, or water, H2O, and they attach by the oxygen and by the nitrogen. And sometimes they're organic compounds, organic molecules that have atoms with electrons to donate. So organic molecules that have oxygens or nitrogens or sulfurs. Again, these organic molecules that have oxygen atoms, so here a nitrogen atom, a sulfur atom, all those can act as ligands. All of those have electronic pairs that can donate to a metal ion to form a complex. And how many ligands are you going to get? Well, it depends on the metal. For example, we call that coordination number, which is how many ligands you're going to have surrounding your metal ion. And you have metals like silver with 1 positive charge, which accepts only 2 ligands, or you have compound atoms or metal ions like platinum that form a square planar. It accepts 4 ligands, and in a square shape. And the most common one, with difference, is octahedral, 6 ligands, so 6 molecules that can donate atoms surrounding the metal ion, that can donate electrons surrounding that metal ion. And this is, for example, how copper is dissolving water as hydrated copper with 6 molecules of water. We follow this complexation, how easy it is for a particular metal to interact with a particular ligand, by looking at something called stability constant or formation constant, which tells you, you know, how difficult or how easy is for that complex to form. You know, the concentration of the product divided by the concentration of the reagents. And that tells you how stable that compound is going to be, how easy it is going to form. And they are defined one by one. So imaginary, you think, I've got my metal ion dissolved, I've got my metal ion, and it gets close to a molecule of water, and, you know, the first molecule of water attaches. Then a second molecule of water comes in. Then a third molecule of water comes in, and so on and so forth. And that, you end up with something called, what is called the overall formation constant, which is the idea that basically, okay, it takes these many steps for a whole complex to form, and the overall, how difficult or how easy it is overall will be dependent on the individual steps. Why do we care about it? Well, because the different metal ions will have different affinities for different ligands. So, for example, in oceans, you have many chloride atoms. Chloride ions is the most abundant of all the ions in salty water. And some metals are particularly good at bonding with chloride and ions. And one of those metals is mercury. So, for example, if you have mercury dissolved in water, in salty water, instead of being in solution with just 6 molecules of water, it will react to acquire chloride ions. So some of those molecules of water will be displaced by chloride ions, and you will form a new complex. So you will still have your mercury dissolving water, but will be in a different form. And why do we care if it's in a different form or not? Well, because tetrachloromercury, which is this complex, is particularly toxic, extremely toxic. So we actually do care, because not all the complexes you form will have the same toxicity. Some will be more toxic than others. And in this case, this is a particular problem when there's mercury in the water. So yes, the tetrachloro species is the principal form of mercury in seawater, which again I was saying it is a problem because it's extremely toxic complex. So this is the end of this series of videos dedicated to the chemistry of water. If you have any questions, please do drop me an email and or post in the chat, in the discussion board, sorry, for the module. Thank you very much for watching, and I hope it was useful.